So we're going to continue working with our first and second derivatives. We're going to start applying them to graphing functions. There's a lot that you can bring to bear in terms of graphing of functions. Most of this handout doesn't discuss calculus. Most of this handout is a reminder of things we've done before in college algebra and in trig. First thing you want to do is look at the domain of your function. Find out if there is any restrictions. Is your function symmetric? That is the left-hand side a reflection of the right-hand side? For rational functions, look for horizontal or oblique asymptotes. You can also find some vertical asymptotes if you have a rational function. If you have a function that has a denominator. Your intercepts, x and y intercepts, are good to look for. So more than half of this handout is done without any calculus. Here's the calculus. Find some critical points where the derivative is 0 or doesn't exist. Look for intervals where it's increasing or decreasing, concave up and concave down, etc. So here's where your calculus is concentrated, and we're going to try and apply as many of these things as we can to try and find the graphs of these functions. Now, I will not be taking away your graphing calculators as you take an exam. So at the very least, make sure your graph, the information you get matches what you see on the graph provided by your graphing calculator. First things first, what's the domain of this function? Yeah, all reals. So negative infinity to infinity, or all reals. So good. Now, there is a little bonus that you could spot here if you were really, really clever and on the ball. If I call this function f of x, you might notice that f of negative x is negative 2 times negative x to the fourth plus 3 times negative x squared. And it doesn't matter if I have a negative x or a positive x to the fourth power. So I can replace that with just the positive values to the fourth power and squared. F of negative x equals f of x. That means f of x is what kind of a function? It's an even function, meaning it's symmetric with respect to the y-axis. That's a feature that I'll be looking for to see on your graph. Of course, you'll see that when you do that on your graphing calculator anyways. All right, there's no horizontal or oblique asymptotes. This is not a rational function. This is a nice warm-up problem. So let's move to some derivatives. Calculating the first and second derivatives. Y prime is going to equal negative 8x cubed plus 6x. Okay, looks good. I want to know where this is actually equal to 0. There's no place where the derivative doesn't exist, but I can find critical points where the derivative is 0. To solve this, I'll factor out, say, a 2x. That's going to leave behind, how about if I factor out a negative 2x? Negative 2x leaves behind, 4x squared minus 3. One of two things is going to happen. If you're going to get a 0 from this, either the first term is 0 or the second term is 0. So negative 2x equals 0, meaning x equals 0, or 4x squared minus 3 equals 0. So x squared is 3/4. X is plus or minus square root of 3/4, or some of you might prefer to write it as plus or minus square root of 3 over 2. Okay, what information does that tell us? Well, these points are your critical points. So let's size this function up a little bit. We've got x, f, f prime. Let's squeeze our critical points in and do a little bit of a test. Try and find out where they're positive, where they're negative, where the function's derivative is positive or negative. So negative square root of 3 over 2, 0, and square root of 3 over 2. I've got some rulers up front if you want to borrow one. Help yourself. At these points, the derivative is 0. I'm also going to want to go back and figure out what's the actual value of the function at these points. And I can do that by plugging in these values of x into the function. For instance, f of 0 is just going to be 0. For these other two, well, I'm probably going to take out my calculator for that. For now, let's program in the derivative into our calculators and do a little bit of testing here. Clear out the old function. You don't have to put it in its factored form here. It's enough to put it in the equivalent form that we calculated originally. So minus 8x to the third plus 6x let's go to the table, delete the old values there. I'm going to need to test some points. Now some of you might recognize it, some of you might not, but these are points that you get when you're working with trigonometric functions. The numerical value of this is about 0.866. Same thing here, 0.866. Why do I mention that? Negative 0.86, yes. Why do I mention that? Yeah, we need test values. So what would some good test values be? Negative 1, negative 1/2, 1/2, and 1. We don't have to stress ourselves and think of something too dramatic. So those would be some good test points. Negative 1, negative 0.5, positive 0.5, and positive 1. What's the relevant information that I want to get out of this? What's the information that I need? Yes? Some help? What do I need out of this table? Yeah, if it's positive or negative. So it's positive, then negative, positive, then negative. What does that tell me? Increasing, decreasing, increasing, decreasing. Okay, nice. Let's find some more information. Your graph should not only match information that you get from the first derivative, but it should also match information you get from the second derivative. So we've got most of the information we need out of the first derivative. There is a couple more things, observations we can make. If the function's increasing, then decreasing, what's the nature of this critical point? Good. It's a relative max. At least a relative max. Could be an absolute max. Don't know yet.
What did you put in for y equals? Because it's not letting me go into the table.
Let me see your calculator. How about this one? What's going on at 0? Yeah, that's going to be a relative min. And then increasing, then decreasing can be a relative max. Looks like it's, you know what? You just got the wrong function in there. But I mean, it's letting me put values in the table. All right, so relative min, relative max. We're going to need to come back and find the coordinates of these points. So I'll want to find those, but I'll hold off on that until I'm all done with this. Let's work on the second derivative. Like I said, this one's a pretty nice one to begin with. The first derivative is a nice polynomial. Second derivative is also going to be a nice polynomial. What's the second derivative? Thank you. Negative 24x squared plus 6. And again, I want to know where this can change signs so that I know where it's concave up and concave down. It'll change signs around the points where it's actually equal to 0. So let's solve here. If this is equal to 0, I'm just going to take this term and move it to the right-hand side. That way I get rid of the negative coefficient. 6 equals 24x squared. Divide both sides by 24. What's 6 divided by 24? 1/4. And then take plus or minus the square root of both sides. What do I get for x? Thank you. Plus or minus 1/2. Let's make another little chart here at plus or minus 1/2. X, F, F double prime, negative 1/2, positive 1/2. Okay, so at these points, the second derivative is 0. But I need to test the value of the function in between these points. Now you can do that by plugging in the second derivative into your calculator and testing points. What would be some good test points here? -1, 0, and 1. Those would be some good test points. You can kind of do this almost in your head, right? I mean, I don't necessarily need to plug in this into my graphing calculator. For instance, at 0, is the second derivative going to be positive or negative? Positive, right? Because it's just going to get a 6. At 1, negative 24 times 1 squared plus 6. I'm thinking that's going to be negative here and negative here. Because it doesn't matter if you square 1 or negative 1. Yuri, what's that telling me about my function? What's it doing? Concave down, up, and then down. Let's do one last thing here in order to kind of complete our work with this. And that is, let's figure out the actual coordinates of these points. And for that, what do I need to put into my calculator? If I want the coordinate when x equals negative 1/2, what should I be plugging into my calculator? The original function. So I want to find values of f. I better put in f into my calculator. That didn't sound right, but put in the function. It's a little bit better. The original function is negative 2x to the 4th plus 3x squared. And we're going to test a lot of points. One of the points I wanted to test was negative the square root of 3 over 2. So negative square root of 3. Press to the right to get out from underneath the square root, and then divided by 2 should give you negative 0.866. And I get a nice y coordinate there. And then likewise with 0 and square root of 3 over 2. And I get some nice y coordinates. So let's write those down. Those all fill in this function here. So 1.125, that's 9/8. 9/8 for both of those. Or 1.125. You know, it's up to you. 1.125. 1.125. Let's do 2 more points. What are those last 2 points you think we're going to do? Yeah, negative 1/2 and 1/2. So negative 0.5 and 0.5. And in both cases, No surprise, I'm getting the same thing. The reason I'm getting the same thing is because it's an even function. So 5/8 for both of these, or 0.625. 0.625. And I think I've got everything I need to graph this. So let's see about the graph then. Well, I can put in a few points. Your graph is on your handout. One of the points I have that I should add is 0, 0. Another point that I can add is at -1/2 and 5/8. So -1/2 and 5/8 is about 0.625. So I'm guessing maybe around here. And likewise around here. Doesn't have to be perfect. Now, one thing that you should keep in mind is that I'm not going to take these wonderful tools of technology away. You can graph these on the test. There's nothing wrong with that. So let's graph this. Can anyone make a suggestion as to what I should set up the window size to be? Yeah, I'm thinking -1.5 to 1.5 and maybe -6 to 2. Sure, match the graph. Why not, right? So let's take a look at our window then. -1.5 to 1.5. I'll change the scale back to 1. And then -6 to 2. Why not? When we graph that, let's see if we can make sense out of all this. So, number one, you see a symmetric function. We predicted that. It has a couple maximum points and a relative minimum point. Okay, so let's play connect the dots. Let's kind of clean this all up. Notice we put in a couple additional points here. So the graph is going to look roughly like this. And you know what? Sorry if you're going to get dizzy. I'm going to spin this around a little bit. Okay, so there's your graph. Yay. Let's label some of these points. This is a max. This is a max. That's a relative min. And these points, what's happening at -1/2 and 1/2? What's of note to us here? Yeah, it's a point of inflection. It's where the concavity changes from concave down to concave up. That's your inflection point. And I'm just going to be a little bit more terse here. Inflection point. There we go. But notice how we combined like a ton of things that we knew in coming up with a very nice and detailed graph. Are we okay with problem number 18 here? Yes. Yes, I'm going to give you the graph. Yeah. So I'm not going to make you draw your own graph. I might make it a little bit bigger, but it'll comfortably fit the graph, and you can show me the features that I need to see. Yes.
The first table that had just
Yes.
what does the 9/8 have to do?
Well, at these values of x is where you had critical points. These are the y values that go with it. So when you plug in -√3 divided by 2, you get the numerical value of 1.125. So that's a point that I plotted on my, actually it was plotted for you, but so this is -√3 over 2, and that height here is 1.125. It's 9/8. And then likewise, this would be positive square root of 3 over 2. And again, it's still the same y height. So they're just plotting those points that I came up with. Okay? Question? All right. Let's see. Which one do I want to do next? There's too many. We're not going to get to them all. Let's do problem number 28. As we do problem number 28, I'm going to show you something you can do at home. Sometimes just to double check yourself and make sure you're not barking up the wrong tree. Y equals 1 over 24 x cubed minus ln of x. I'll also consider that as f of x. I hope that one thing that you've gotten out of this course is a good habit of thinking about the domain of these functions. This one's going to have issues, unlike the last one. What do we have to be careful about relative to this function? Yeah, can't be negative. Has to be positive. Can it be 0? Log of 0 is not defined. So, has to be strictly positive. So your domain is 0 to infinity, but that 0 gets a parenthesis because you can't take the log of 0. This is not going to have any horizontal asymptotes. It's not a rational function. It's not going to have any symmetry. You're not going to have any y-intercepts. You can and probably will have some x-intercepts, but you'd have to pretty much determine those numerically. And I'm not going to make you do that. If it's something easy, okay, like factoring a quadratic equation or a linear equation, that's fine. But I'm not going to make you solve this. You'd have to use like Newton's method. So let's jump down a little ways then. We need to figure out some derivatives here to start working on this. Figure out where there are maximum points, minimum points, inflection points, etc. Let's start with y prime. What's the first derivative here going to equal? Yeah, go ahead. All right, good. So you're going to get 3 over 24, or better yet, 1/8 x squared minus what? 1 over x. So I'll rewrite that as 1/8 x squared minus 1 over x. It might be in our best interest in this one to get a common denominator. X squared over 8 minus 1 over x. That way I'll have a numerator and a denominator, and I can look where the function has a derivative that doesn't exist or is equal to 0. In order to bring these two terms together, I need a common denominator. What's a common denominator for these two terms? 8x, good. So I'll multiply the first one by x over x, and the second one by 8 over 8. So I get x cubed minus 8 all over 8x. Okay. I need to know where this equals 0 in the numerator or equals 0 in the denominator. Because at either of those two places, the derivative can change sign. It can go from positive to negative or negative to positive. So, part A here, the numerator equals 0. That's going to be x cubed minus 8 equals 0. Nothing fancy here. I'll take the cube root on both sides. What could x equal? 2. The denominator equals 0. Well, that's just 8x equals 0. That's pretty easy. X equals 0. But there's a problem here, right? Well, a little bit more than that. 0 is not in the domain. So if it's not in the domain, then that's not going to be a critical point, right? Because there's no There's no place on the graph that corresponds to x equals 0. So that's pretty nice in terms of our little table here. There's not a whole lot we have to fuss with. Draw ourselves a little bit of a graph, or a little table here. X, F, F prime, and 2. So at x equal 2, the derivative is 0. I'll have to go back and figure out what f is. I need to test points on either side. So what will be some good test points here? 1 and 3? Sure, 1 and 3. You can plug in the derivative into your calculator and test them that way. Let's just see if we can't think about it. At 1, I'll get negative 7 divided by 8. You know what? That's negative. Cool. At 3, 27 minus 8 divided by 24, I'll have a positive divided by a positive. I don't care exactly what the number is itself. What's that telling me about my function here? Decreasing, then increasing. Now to get the second derivative and work on the concavity, concave up and concave down, well, what do I have to do to get the second derivative? Quotient rule, f prime of x. Let me show you something you can do at home. You're not going to be able to do it on an exam, but you can do it at home if you're like struggling, if you keep on getting the wrong answer, you're like, oh, I don't get it, what's going wrong? And it's go to Wolfram Alpha. So, wolframalpha.com. And in order to calculate a derivative, what you need to do is you need to type in a command of this form. DER, so derivative of f of x, comma, x. You have to tell it what you're differentiating with respect to. So, let's try it. DER of x raised to the third divided by 24 minus ln of x, comma, x. Of course, this is just the first derivative, right? I need the second derivative. Isn't that special? They did exactly what we did. Now, here's where I get a little bit clever. I don't feel like trying to type this in. So here's what I'll do. I'll type in DER, parentheses, and then go over here, comma, x. So the derivative of the derivative. Ha ha. All right, so, and it's going to come up with the second derivative. Thank you very much. All right, so 1 over x squared plus x over 4. All right, so 1 over x squared plus x over 4. That's our second derivative, y double prime. We're going to play the same game here that we did with the previous one. Yes, sir?
You can go to Sci Math, it's like CY Math, and they do the same thing but show you all the steps.
CY Math?
Yeah.
Let me check that out. CY Math?
Yeah, you can Google it, but
Okay.
you gotta click choose topic and then derivative before you type it.
Oh, okay.
You type something in and then say derivative, it'll tell you what you typed in.
Derivative? All right, tell you what, I'll let you guys play with CY Math. You can't just do, can you type in derivative here? Derivative?
No, you might be able to do that, but you say choose topic.
Okay, let me just try it here. Derivative of, let's do x cubed minus 8 divided by, now I need to put this in parentheses, 8x, comma x. Oh, wow. So it's showing you the steps. It's looking different. Oh, all right. Well, let's see. I typed in an x cubed here by mistake. It looks like. No, wait. 2. All right. It's just regarded that as 2 cubed. 8x. Um. Hmm.
I think it's when you solve it, not you solve the derivative.
Yeah, at the bottom it says ER or EDR.
Yeah. All right. So. All right. Let's trust. All right. Let's trust. Put our trust in Wolfram Alpha for the moment. This looks like something that we should check out. So. Oops. You know, it's cool that you can see all the steps, and if you go pro on Wolfram Alpha, then you can see all the steps. So let's go back to our second derivative then. Like the first one, we're going to get a common denominator here. Common denominator is going to be 4x squared. So I'll multiply the top one, or the first one, by 4 over 4, and the second one by x squared over x squared. So I'll get 4 plus x cubed over 4x squared. Now this can equal 0. It can change signs where the numerator equals 0 or where the denominator equals 0. So numerator equals 0 when 4 plus x cubed equals 0, which means x equals the cube root of negative 4. And the denominator equals 0 when 4x squared equals 0 or x equals 0. Well, that's going to make our life easy. Both of these are outside of the domain. So, okay. Basically, the second derivative is either always going to be positive, always going to be concave up, or always going to be concave down. It's not going to be both. So what's that going to give us then? Well, let's do a little test here. X, F, F double prime. I'm not going to put a point in here. Well, let's see. I can put in 1, I guess. Let's put in a 1. At 1, what do you notice about the function? The derivative here has to be positive, or second derivative has to be positive. So this should be concave up for the entire function. So the only point that really is of much consequence for us is where x equals 2. And at x equals 2, if you put it into your function, you're going to get 1 over 24 times 2 cubed, which is 8. 8 over 24 is going to be 1/3. 1/3 minus ln of 2. So I'm going to need a decimal value for that. Let's figure that out, and then I think we should be in good shape to graph this. So 1 divided by 3 minus ln of 2. Negative 0.36. All right, I'm not going to look at your graphs that closely. Negative 0.36. See, that's a 1. So that'd be negative 0.5. So about here. Somewhere just below the 2 on that graph. For the rest of it, let's just look at our graph. See that what we see from our calculators matches what we see when we do the calculus. So I'm going to graph x cubed over 24 minus the ln of x divided by 24 minus the ln of x. What should I set up my window as? Yeah, I'm thinking maybe 0 to 6 and 0 to 6. That works pretty good. 0 to 6 and 0 to 6. Yeah, maybe we should go to a little bit below there. Yeah, negative. So negative 0.5. There we go. Thank you. Beautiful. Oh, here's another way that you can get a decimal value for what happens at x equal 2. Hit the trace key and then type in a 2. And there you go. There's the y coordinate, negative 0.36 roughly. Does this match what we saw? Yeah, we've got a minimum point here. We've got a concave up shape forever. So let's try and graph that. It's going to look roughly like this. It'll never quite touch the graph here. It'll always be really, really close, but it'll never quite touch the graph. So there's your minimum point, and this is concave up. How are we looking on 28? Question? Actually, if you wanted to be very accurate, this is an absolute min, because the function can't get below this. It's decreasing till this point, and it starts increasing. If it was going to start decreasing and get below this, what would have to happen that we don't see happening? If it wanted to turn around and start coming down to get below this minimum point, yeah, you'd have to have, you'd see a change where the function had a horizontal tangent. It's going to change its shape and start heading down. It'd be another interval over which the function is decreasing. We've only found one interval where the function is decreasing. So since it's increasing to the right of 2, it can never actually get back down below that point. So good question. All right. Anything else on 28? We're going to do kind of an experiment here. I'm kind of curious. We're going to do this one numerically, and that's really kind of what they're asking for in this problem, is for you to do this problem numerically. I've got it written as problem number 18, and I'm sure that it is problem number 18. Let's just double check. I think it's in the 40s. Does anyone see that problem? 36. Yeah. So it's 18 times 2. That's the problem this one is. All right. Nice. Good save.
That looks like 18 with the x squared.
It does. It does. All right, fine. Fine. Here. Put the 2 in front of the parentheses. I don't have any whiteout. Here. 2 times 18. There we go. Better. Oh, that's actually the real problem number 18. All right, forget it. Let's just stick over here. Now, put this into your calculator. And then let's take a look at a couple windows. What we're going to do is numerically, or just kind of graphing and looking at the graph, try and pick out some features, minimums, maximums, and inflection points. Now, I've given you 2 views of this. Here's a little bit of a zoomed out view. And you kind of see that this graph has a horizontal, or actually an oblique asymptote. Let's see if I can't. Yeah. It'd be along this line here. So along this, I mean, this function is going to eventually get close to the line y equals x. Can you see why that would be true? What's going to happen if you put in bigger and bigger values in for x? What's going to happen to this? It's going to get really, really small. eventually it's going to be almost like 0, so you're going to be looking at the graph of y equals x. So that's why this has an oblique asymptote. But plug this function into your calculator, and let's just kind of surf around and see if we can't estimate some of the mins and maxes. So x plus, let me remind you, in case you have a calculator that's up to date with the latest operating system, if you hit the alpha key, then the y equals key, you can type in fractions. And that makes it easier to put in things rather than do 4 divided by parentheses x squared plus 1. I don't have to worry about the parentheses here. And if you don't have that, then the brute force approach is 4 divided by parentheses x squared plus 1. Like that. Either way, let's set up the larger of our two windows, the more expanded one. I'm going to shut this graph off. I don't need to see it twice. So for a window, I'll start with -4 to 4 on the x-axis and -3 to 5 on the y-axis. Let's see what we get. So it's got a little bit of a dip right here to the right of the x-axis, the right of the y-axis, and then a relative maximum there. I think you can spot where the relative maximum is. What's the relative maximum of this function? What are its coordinates? Yeah, you don't even have to think that far. Trace and then 0, right? 0, 4. So 0, 4 is a maximum. That doesn't look right there. No, it's not quite a maximum. It's just your y-intercept. 0, 4 is your y-intercept. It's not a maximum, though, is it? Tricky. Watch out. So you could and should look at this with the derivative, but here the idea is to look at it just using your graphing calculator and try and estimate some things. So let's maybe zoom in a little bit, because the interesting part of this function is right here, right? Now, one way you can zoom in is just by adjusting the window, or then there's the zoom box feature. Have we done zoom box? Okay, so zoom box, and we're just going to adjust the window a little bit. Choose kind of a tight box around here that zooms in a little bit more. So I'm roughly at -0.6 and around 2. And let's zoom in. That looks pretty good. I'll make it a little bit tighter. Yes, sir.
How do you do that on the 83? Or can you do
Yeah, you can do that on 83. Just hit the zoom key, and then the first option should be zoom box. Okay, so let's cursor over here. So hit the trace key, and then move over. What kind of a point am I getting at near here? That relative max. You can actually find the exact value of that relative max with the calc key. Hit the second key, then the calc key, second in calculus. Does it look like something here that might be helpful? Maximum. To find the maximum, just go a little bit to the left of your maximum point, and then press enter. And then to the right of your maximum point, and press enter twice more. And there's your maximum, 0.129. You like that, or are you smiling at something she said? Which one? All right, so you're giving yourself a little atta girl? Okay, good job. And then likewise, you can do the same thing with the minimum point over here. So second calc, and then this time I want a minimum point. Let me just get a little bit closer. In fact, you can just type in a number like, I don't know, 1.25. And then let's type in another one, say 2. Let's see, 1.5. I don't know. I forget the scale here. Do I have it in units of half? Yeah, let's go for 2. Yeah. And then press enter. So 1.6. So 1.608. That's my minimum. Of course, you can get the y coordinate there as well, depending on what you need. We've got the maximum. At some point in between here, what other interesting feature do I have? And it's kind of tough to estimate. I mean, it's a little bit of a guess. What other interesting thing is going to happen between this maximum and this minimum? Point of inflection. So the function is concave down until some point, and then to the right, and from on out, it's concave up. Notice my subliminal message here? Yay, go blue. All right. But right here, I mean, roughly, the concavity changes. So you're going from concave up to concave down. So tough to estimate what point that is. Let's do it here on the graph. So it's not showing up too good. It's where the second derivative changes sign. Yeah. So somewhere about here. I mean, if I gave it a problem on the test to do it numerically, I'd have in mind a range of values that I'd accept. But they would have to be somewhere between, say, here and here. What I get a lot of times is people want to say that the concavity changes at the maximum. No, it doesn't. It's still concave down at that maximum, and actually beyond that maximum till some point over here. So don't say that the concavity changes with a maximum or minimum point. Here it's concave up, a little bit to the right, a little bit to the left. It's still concave up. It doesn't change at those points. Okay. So the last one we did kind of numerically. Any questions on that part? Nope. No, sorry. I will bring this back in terms of one last calculation, and it's one that I relied on Wolfram Alpha for in my morning class, just to fill in a little bit of a hole there. I want to calculate the second derivative of a function that's one of the ones that's on your handout. So it's problem number 12. And really what we're doing here is we're finishing up by calculating or practicing some more work with our derivatives. So for the rest of this on problem number 12, you're going to have to catch the video from the morning class. What we're going to start with, though, start with a function. This is problem number 12. F of x is, where is it? Rats. F of x is x times the square root of 9 minus x squared. We noticed in my morning class that the domain has to be between -3 and 3. Most of you would probably rewrite that as 9 minus x squared to the 1/2. That's fine. The first derivative was the very friendly 9 minus 2x squared over 9 minus x squared to the 1/2. Let's work on the calculating the second derivative together. It's not really pretty, but let's see what we can do. The 1/2 and the 2 are going to cancel each other out when you apply the product rule. When you apply the product rule. So you're going to have a chain rule that's going to give you a minus 2x, but there's going to be a 1/2 that comes out in front. All right. Good question, though. So let's work on f double prime of x. We'll start with the square of the denominator, So this to the 1/2 power gets squared. And then the denominator, 9 minus x squared to the 1/2, times the derivative of the numerator. So far, so good. The derivative of the numerator is not that bad. What is it? Negative 4x minus. And always put that minus down before you start doing any calculations. Want the numerator, 9 minus 2x squared, times the derivative of the denominator. So the derivative of the denominator, okay, so that's going to be 1/2 times 9 minus x squared to the negative 1/2. That's the derivative of the outside times the derivative of the inside. Negative 2x. So a lot of mess we need to clean up here. I'm going to write this out in front. Negative 4x times 9 minus x squared to the 1/2. A careful look at this shows I've got a negative here and a negative here. Those will cancel and give me a positive. The 1/2 and the 2 will also cancel. So I'll get an x times 9 minus 2x squared. And then just a 9 minus x squared to the negative 1/2. In the denominator, the 1/2 and the 2 cancel each other out, so I'll have 9 minus x squared. Let's just double check this before we go on. This is where it's nice to have Wolfram Alpha Pro, which I don't, because then it shows you all the steps. Derivative of the numerator minus the derivative of the denominator, so denominator times the numerator, so there. That looks good. Half, negative, negative. It looks good to me. How about you guys? Has anyone seen any mistakes here so far? Now there was a big trick that we practiced 4 times last week, or last Tuesday. What is it that I'm going to factor out now? Yeah, this term right here. Some questions in the back, gentlemen? It's the derivative, it's the denominator times the derivative of the numerator. So that's the derivative of the numerator. Derivative of 9 is 0. Derivative of that's going to be the minus 4x.
Don't you put like the derivative of the numerator times just the regular denominator minus the regular numerator times the derivative of the denominator? Like for the equation? Like you have the derivative of the numerator times.
No, it's the derivative of the numerator times the denominator is exactly what we have here. So this is your denominator, 9 minus x squared to the 1/2 times the derivative of the numerator. So what's the derivative of the numerator? It's just minus 4x. Minus 4x. And that's what we got. Minus.
Oh, the first term is the denominator. Oh, okay. I thought it was the numerator. Why do you have to?
Okay. Justin? Okay. This is the term that needs to get factored out. So, this gets a little bit tedious here. I understand that. That's why I only put like 6 or 8 of these on an exam. All right. We've got 9 minus x squared to the negative 1/2. That's going to divide each of these terms here. Now, some of you can do this in your head. And if you can do it in your head, if you can skip this step and write the next step, power to you. I write it down so that people can see it and follow it. If you don't need to write it down, you don't have to. You're not getting extra credit for writing it down. Plus x, 9 minus 2x squared, 9 minus x squared to the minus 1/2 over 9 minus x squared to the minus 1/2. Divided by 9 minus x squared. And that's to the first power, essentially. Okay. So some nice cancellation here. This term and this term are completely gone. what happens here? Yeah, it's just you get this to the first power because the 1/2 minus negative 1/2, those add, change the signs and add, you get to the first power. This, I'm going to put down in the denominator. So it's going to look like this. Negative 4x times 9 minus x squared to the first power plus x times 9 minus 2x squared over 9 minus x squared to the 1/2 power times 9 minus x squared. Almost done. Got a little bit of cleaning up to do in the numerator. If we distribute this negative 4x, I get negative 36x plus 4x squared, no, 4x cubed, plus 9x minus 2x cubed, all over 9 minus x squared. Let me rewrite that. 9 minus x squared to what power? 3/2. You can add their exponents. 1 plus 1/2. 3/2. Almost done. Take a deep breath. So the last thing to do here is to add up the like terms. 4 minus 2 is 2. So 2x cubed minus 27x over 9 minus x squared to the 3/2. Woo! Nice. Nice, nice. Okay. Yeah, easy for me to say, right? Let me give you some homework. For homework, try 1 through 29 and 35 through 39. So I threw in a couple numerical ones there. So homework, section 4.6, 1 through 29, and 35 through 39? See ya!